Hi, I'm Takuma Habiro from Okayama University of Science, Japan. I would like to have a presentation at the proposal to measuring and control system of flexible pneumatic actuator using a wire type and potentiometer. This is outline of my talk. First, I will explain the background and purpose of our study. Secondly, I will show the improved spherical flexible pneumatic actuator, SFPA for short. Thirdly, I will show you the active control of spherical flexible pneumatic actuator using a simple sensor. Finally, I will give you our conclusions. In recent years, with the progress of the aging society, healthcare supporting devices that can give passive exercise to injured joints to maintain the moving range of the recovered joints treated by physical therapists is desired. In previous study, we developed a spherical flexible pneumatic actuator using switch chamber for voluntary wrist rehabilitation. In this study, we aim to improve to allow more precise control, bending directional angle, and higher rigidity. We also aim to develop simple and low-cost attitude control system. I will show you the improved flexible pneumatic actuator. This is an extension type flexible pneumatic actuator used in Spherical Flexible Pneumatic Actuator. We call it EFP for short. The EFP consists of a silicone rubber tube covered with a below-type nylon strip and two plastic end connectors with a supply port. The operating principle of EFP as follows. When the EFP is pressurized, the rubber tube expands. However, because below-type strip restrains axial moments, it extends only in the axial direction until about twice of the natural length. Then the maximum pulling force of EFP is 16 Newton. Next, we will explain the usage image of target device using EFPS. As a voluntary rehabilitation for wrist to maintain the recovered moving range by treatment by physical therapy, the ball exercise is well known. In order to give passive exercise by putting hands on the device like this, the device need to perform a radial translation and rotational motion along spherical surface. Therefore, we develop a spherical flexible pneumatic actuator using EFPS. We call it EFP for short. This figure shows the previous SFPA. The previous SFPA consists of 3 EFPs restrained by PET sheet so as to make it rugby ball shape. In this study, in order to increase bending stiffness and operable bending directional based on-off pressure EFPS, the SFPA using 6 EFPS was developed. Next, we will explain the construction of the improved SFPA. The improved SFPA consists of 6 EFPs arranged parallel every 60 degrees from the center and 13 restraint plates so as to form the rugby ball shape. The right figure shows the setting radius of EFPA and restraint pad sheet number. Blue and red symbols show the setting radius of EFPA in the previous and improved ones. You can see that the maximum setting radius of EFPA in the previous SFPA is 72 mm, which is about 1.3 times larger than the previous one. By the improvement, the improved SFP can get higher bending rigidity and vertical rigidity when SFP bend. Figure shows the relation between the applied pressure and bending angle of the SFPA when pressurized EFPs were changed. Each color indicated the number of pressurized EFPs. From the result, we can see that bending characteristics are similar when 3 and 4 EFPA are pressurized. However, when the 4 EFPs are pressurized, the particle displacements become more longer, which is not suitable for bending motion. When the one EFPA is pressurized, it does not provide a sufficient bending angle. Therefore, we confirm that pressurized 2 or 3 EFPA is suitable to control the bending angle to give passive exercise motion. This table shows the relation between bending directional angle and pressurized EFPs in the previous and improved SFPs. pressurized EFPAs are marked green bar. The previous SFPA could bend in 6 directions every 60 degrees by applying pressure to 1 or 2 in the 3 EFPAs. By increasing the number of EFPAs to 6, the improved SFPA can bend 12 directional, uh, sorry, uh, 12 direction every 30 degrees by pressurized 2 or 3 EFPAs. This figure shows that a previous active measuring system of SFPA. In the previous system, by measuring a part of center length of the SFPA by using Hall sensor and ring-shaped magnet attached with the end of SFPA, Hall extension length and bending angle were estimated. However, this method is more affected by disturbance force. This figure shows the transient response of the bending angle when the SFPA traces a certain bending angle of 60 degrees. In the experiment, a hand of pressing on top of the SFPA, while the bending directional angle was switched every 4 seconds. As the previous measuring method is easily affected by vertical rod, the SFPA could not trace the desired bending angle because of detected error. Therefore, in the study, we measured the whole actual length of SFPA. The left figure shows a wire-type linear potentiometer that consists of 10-turn helical potentiometer, wire winder, and wire. By penetrating with the wire to the center hole of SFPA, the sensor can measure the sensor actual length, even if the SFPA bend and extend. The figure shows a definition of the bending angle and radius of curvature. The right upper and lower figure show that relation between the measured actual length and bending angle and radius of curvature respectively. Red and blue symbols show the result when 2 and 3 EFPA were pressurized in bending motion respectively. From the right upper graph, we can see that pressure relation between actual displacement and bending angle is almost linear. Furthermore, from the lower graph, we found that various curvature converge to a certain value. It means that the SFPA can move on a spherical surface. The figure shows the schematic diagram of improved active control system of SFPA. The system consists of improved SFPA, 6 3-port type on-off valves connected by EFPA stores to make a common chamber with a pressurized EFPS, 2-port type on-off valves for air supply and exhaust that connected to the common chamber, an embedded controller, and the wire type linear potentiometer. Active control flow is done as follows. First, the controller receives a call through Bluetooth from a tablet. The controller sets to drive on valves according to pre-installed sequential program and desired bending angle based on transmitted code. The sequence program is set to change 12 bending direction every 3 seconds. I will show you the result of active control using a proposal system. The control scheme of bending angle. An on-off control scheme with dead zone was applied, as shown in this figure. A dead zone of plus or minus degree from the desired bending angle is set. If the deviation is within the dead zone, it is maintained. Otherwise supply or exhaust operation was checked based on negative or positive value of error. This video shows the result of tracing active control with a constant desired bending angle of 45 degrees. The figure shows the restraint response of bending angle. In the response, the red broken line shows the desired bending angle, and blue line shows the control bending angle detected by the sensor. We can see that control bending angle remains within plus or minus 2 degrees from the desired angle of 45 degrees. You can see, we, when switching the bending directional angle, and spike error occurs due to modeling switching. Also, you can see that the larger spike error is appears when switching the bending direction angle. However, from the video, we can observe a large error or sudden motion. Therefore, we confirm that the error is related to modeling error when the calculated model is switched. These figures show the result of tracking control in case when the desired bending angle is set 60 and 75 degrees respectively, as same as the result for a bending angle of 45 degrees. We can see that both control bending angle were within plus or minus 2 degrees from the desired angle. The video and response show the result of tracking control when the bending angle is changed from 30 degrees to 75 degrees every 7.5 degrees. You can see that the SFPA can trace the target bending angle relatively well. This study can be summarized as follows. To improve the rigidity and generating force of the spherical flexible pneumatic actuator and increase operable bending direction with on operation, we propose a test and improve SFPA using parallel around 6 EFPAs in a rugby ball shape. As an active measurement system, the method to measure whole axial length of SFPA by using the wire-type random potentiometer was proposed. The active control system of the SFPA using a minimum number of the valve and tested sensor was proposed and tested. As a result, we confirmed that the attitude of the SFPA could be controlled relatively well by using simple on-off control scheme. Thank you very much for your attention.